Alright, in this video we're going to talk about stereocenters and how to predict whether they are R or S. So once you've been able to show that you can actually predict in a molecule where stereocenters are, in some cases we have to be able to tell their stereochemical designations. Now you will have seen the terms cis and trans before. You'll see those in alkenes and cycloalkanes like cyclohexanes. But there are other stereochemistry terms that you guys need to know. For example, take a look at these two molecules here. You can see there's an alcohol, there's an ethyl group, there's a methyl, and there's a hydrogen. And these two are in the plane of the board. The methyl's coming towards you, the hydrogen's going away from you. And then take a look at this molecule, and if you ask yourself the question, well, what's the relationship between these two? You'll notice that they appear to be, if you assume this thing here is a mirror plane, you'll see that they appear to be mirror images of each other. Okay? They are mirror images, and they're non-superimposable. That means I can't take this structure and stick it right on top of this one. That means they'd be non-superimposable. The term for these two compounds, and we'll see another video about this later on, the term for what these two compounds are related as is called enantiomers. Now, the important thing about this is the fact that the chiral carbon in each of these molecules, which, as I'm sure you can tell, is the one that I've starred here in each case. This is the chiral carbon in each case. And these enantiomers have exactly the opposite stereochemistry, and R represents one stereochemistry and S represents another. These letters really mean the way these molecules rotate, plane, polarize light, which, as far as you guys are concerned, just means to do with the priority of the groups around the chiral carbon. So I'm going to show you how we can figure out if a particular stereocenter is a chiral carbon, one with 4 different groups attached to it, if we can figure out if it's R or S. And we're going to do it for a variety of compounds. So these are two enantiomers. They have opposite stereochemistry, so we're going to find out that one of these is R, and we're going to show that the other one is S to indicate that they are in fact opposite. So the way we go about this is we have to make sure, first of all, that our compound is oriented in the right way. Our lowest priority group has to be pointing away from us, in other words, on the dash. So we should talk a little bit about the priority rules. Priority rules are based on atomic weight of the group directly connected to the stereocenter, the chiral carbon. And I'm just going to underline all 4 of the atoms concerned, directly connected. All right? Can you see that's carbon, carbon, hydrogen, and oxygen? Hydrogen has the lowest priority, so we're going to assign that priority number 4 being the lowest. All right? And then we have to ask ourselves, well, which of the remaining 3 has the higher priority? Is it oxygen, carbon, or carbon? Well, in terms of atomic mass, oxygen's higher than carbon, so therefore oxygen gets priority number 1. So what about these two? Because they're both carbon, how do we assign the relative priorities? Well, if we can't assign priority based on the first atom we come to, we move to the next biggest one connected to this. In the methyl group, this carbon is connected to 3 other hydrogens, so the next biggest atom is hydrogen. This carbon is connected to these 2 hydrogens and this carbon, and because carbon is bigger than hydrogen, the ethyl group has higher priority over the methyl, and so our order of priority is like this. So can you see that we have organized the priority of all our 4 groups? The lowest priority group is already pointing in the direction we want it to. It's pointing away from us. And all we do is look at the priority of the others and see which order we have to go to count 1, 2, 3. Now, if you notice here, going from 1 to 2 to 3, I have to go around counterclockwise. Alright? Now, going around counterclockwise means your stereochemistry is S when you count round in a counterclockwise fashion. Now let's move over to this one, just so you can see that this is going to be opposite of this guy. The groups are exactly the same as they were here, so I'm going to assign exactly the same priorities. 1 for the oxygen, 4 for the hydrogen, 2 for the ethyl, and 3 for the methyl. Now notice how I'm counting this time. Here, the arrow is going around the way the clock goes. This is going around in a clockwise fashion. All right? When you go from 1 to 2 to 3 in a clockwise fashion, going around like this, your stereochemistry is R, and that's how you can see that these two are exactly opposite to each other. Now let me show you how to do this on some other compounds, okay? So let's take a look at this one. All right, this one's quite similar to what we had before. The first thing we always have to do is make sure, first of all, we can see where the chiral carbon is, and the chiral carbon is right here. Hydrogen, if it's present, is always going to be the lowest priority group. So we have a methyl, we have an ethyl, and we have an iodine. Now iodine's pretty big atomic mass-wise, so that's going to be number 1. For the same reason as we saw before, the ethyl has higher priority than the methyl. Therefore, when we go around here, we go counterclockwise. The stereochemistry about that carbon is S. Now when we come to this molecule here, in some cases you're going to find molecules where the stereochemistry, where there's more than one chiral carbon. There's a chiral carbon here and one right next to it. All the other carbons are not chiral. So we're just going to do each one separately. And I'm going to use different colors because otherwise it can get a bit confusing. So we're going to focus first on the carbon on the left. There's a methyl, a hydrogen, an OH, and all the rest of this stuff. Hydrogen, of course, has the lowest priority. And this is the stereo center that we're looking at. So connected to that is an oxygen, a carbon, and then this carbon here. Now oxygen's got the highest priority out of, oxygen's got a higher atomic mass than carbon and carbon, so that's going to get number 1. So the question is, between the methyl and all this, which one's got the higher priority? Well, connected to this carbon is just 3 hydrogens. Connected to this carbon is other carbons and a sulfur, so this group definitely has priority over this one. Therefore that's going to be 2, and the methyl is going to be 3. So when we go around, bear in mind we're still focusing on just this carbon. The stereochemistry about that carbon, when I go 1, 2, 3, I'm going counterclockwise just like I did here. So this stereo center around this carbon is S. Alright? Now I want to try and avoid confusion if possible, so I'm going to do this carbon in a different color. Alright? So this is the stereo center that we're thinking about, and so notice there is no methyl group, and there is no hydrogen here. We've got a SH, a CH3, a CH3, this is an isopropyl, and then all this stuff. So the question we have to ask ourselves in this case is, which of these 4 groups, this one, this one, this one, and all this, has the lower priority? Well, sulfur has a higher atomic mass than carbon, carbon, or carbon. Therefore, this guy has priority number 1. Okay? Here the carbon's connected to 3 hydrogens. Here the carbon's got a hydrogen and 2 carbons on it, so this guy has higher priority than this. Now this carbon here has oxygen connected to it. Now oxygen's bigger than carbon, so therefore all this group has priority number 2 around this carbon. We know that this group has higher priority than this one, therefore this is 3, and the methyl is 4. The methyl is already pointing away from us on the dash. It's the lowest priority group, so we don't need to do any rotation. And when I take my arrow and go around 1, 2, 3, can you see I'm going around clockwise? So therefore that means the carbon on the, I'm sorry, that's not S. See, I was just checking to see who's actually watching. That's not S at all. Going around clockwise is R, counterclockwise is S. So here, the carbon on the left is S, the carbon on the right is R. Alright. Now let's take a look at this one. Alright. This is a molecule that's obviously cyclic, and we're going to ask ourselves, well, how many stereocenters do we see here? Well, I got a CH2, a CH2, a CH2, a CH2, and none of those are chiral carbons. I got a carbon with 2 CH3, so that can't be chiral either. The only one that could possibly be is this carbon. So we've got to ask ourselves, well, what's coming off this carbon? Well, there's a CH2 or CH2. There's a CH2 and, well, that's not a CH2. Can you see this molecule does not have any symmetry down the middle? So therefore the stuff on this side is different to the stuff on this side. And therefore we can count this side of the ring differently to this side. Now the other group coming off this carbon, of course, is the hydrogen. So I'm going to draw that on. You don't necessarily have to draw it on, but it's always useful for you to do so if you feel the need to. Let's think about priorities again, okay? We've got oxygen. Again, this is the stereocenter. We've got oxygen, hydrogen, carbon, and carbon. Now, oxygen's got the highest priority, so that's going to be priority 1. Hydrogen's going to be priority 4 because it's the smallest. We've got a CH2 and a CH2, so we can't make any difference there. When we go up to the next biggest atom, we've got a carbon with 2 hydrogens on it. And this carbon has 2 carbons coming off it. So therefore, can you see going up this way has a higher priority than this way because of these 2 carbons here. So therefore, that means this side is going to be priority 2, this side is priority 3. This side has the higher priority. The hydrogen is already pointing away from us, so when we go round with our arrow, can you see we're going in a counterclockwise fashion? Therefore, what's the stereochemistry at that carbon? Well, it is S. All right. Now, let me go through one more thing here. What if I wrote something out like this? I'm going to draw out a tetrahedral carbon here. And what if I did something like this? I'm going to do a H. I'm going to do an OH. I'm going to do a CH3. And I'll do, say, a Br. All right. And the question then is, just as before, what's the stereochemistry? Is it R or is it S? Now, let's do our priorities, okay, same as we did before. Bromines, they've got the largest atomic mass out of all of these, so that gets priority 1. Hydrogen gets priority 4, because it's the smallest. Oxygen has higher atomic mass than carbon, so therefore, although it's smaller than bromine, it's bigger than carbon, so it gets priority 2, and carbon in the methyl group gets priority 3. The thing we have to be careful about this is, notice in this case the hydrogen is not pointing away from us, it's actually pointing straight up. Now the book tells you, and most books tell you this way, to try and visualize it so you're looking down the carbon-hydrogen bond so it's pointing away from you. Now for a lot of people that's kind of tough to do, so what I'm going to show you is what I like to call the Pennington method of how to make this a lot easier for yourself. So here's what I would recommend that you do. It's much easier to do this than anything else, at least I would say so. First thing you should do is write out the stereocenter again, just as it was before, except don't put on any of the groups. All right? We're going to treat this molecule like an umbrella. All right? We're going to grab onto one part of the molecule and twist around one of the bonds so we can get the hydrogen to go in the position we want it to go in. Okay? What I usually like to try to tell people is grab onto one of the atoms that's in the plane of the board. Grab into one of these 2 bonds. So in this case, we're going to grab onto the bromine. Imagine that we put a clamp on this bromine here. That's my fabulous rendition of a clamp. And we're going to rotate around this bond. We're not going to rotate around this bond because we want the hydrogen to move. Okay? So the idea is we are rotating around here, and we have to figure out, well, where is everything going to go? And it turns out there is a way for us to do this that doesn't involve any guesswork at all. So if you think about it, if you're clamping the bromine, there's no way the bromine can move, so we're going to leave that where it was. Oftentimes people have a really hard time figuring out where the other 3 groups go, but if you do this one simple trick, it's much easier. Tell yourself you know one of these groups, you know where it's going to go. You want the hydrogen, the lowest priority group, to go on the dash. If you can tell yourself that, putting on the other 2 groups is actually a piece of cake. Because if you rotate around this bond, can you see that none of these 3 groups can stay in their original positions? If the hydrogen moves, then that means these 2 have to move as well. So if the methyl was originally on the wedge, can it be on the wedge after the rotation? Of course the answer is no. And if there's only one other spot for it to go, then that's up here. And then that takes no guesswork about what goes here. It must be the OH. Notice that all the groups apart from the bromine have all changed positions, which is what you want. If we now put on the priorities, just as we did before, all right, I'm not changing any of the priorities, I'm putting them all exactly where they were before. Now the hydrogen is where we want it to be, and we can say, well, we're going to do our 1, 2, 3 to see which way we can turn. We can't effectively do this until the lowest priority group is pointing away from us. And if we do that, can you see that after we've rotated and we go 1, 2, 3, we have to go counterclockwise, so therefore that means the stereocenter here is S. Now some of you may be able to see this, visualize it without doing this rotation, but in my experience a lot of people have a hard time doing that. I have a hard time doing it myself, so I like to do this rotation because this takes any representation of atoms that you have here and makes it easy to convert it into the one you want, provided that you remember the lowest priority group always has to go on the dash. And that is how you can figure out whether stereocenters, chiral carbons, are R or S.